Algebraic manipulation for substitution. Okay, so let's move on to a slightly more challenging aspect of integration by substitution. As you recall from our previous lessons, we've been learning how to spot opportunities for substitution, that is, identifying a function and its derivative within the integral itself. We were able to directly recognize them. However, as we tackle more complex integrals, especially in advanced problems, things aren't always so straightforward. Often, that clear relationship between the function and its derivative isn't immediately obvious. It's hidden. That's where a crucial technique comes in: algebraic manipulation. What this means is that before we can even think about applying substitution, we sometimes need to rearrange or transform the integral using things like trigonometric identities, things you've learned in trigonometry, or just clever algebraic tricks. Think of it as preparing the integral. We need to manipulate it to reshape it, to make that function and its derivative become visible, so that substitution becomes possible. This slide is setting the stage for what we'll be doing in the following slides, learning how to do this manipulation, and then applying it to solve some tricky integrals. We'll be looking at specific examples, starting with one on the next slide, to show you exactly how this works in practice. Understanding the concept. Algebraic manipulation is similar to preparing ingredients before cooking. Think about it, you wouldn't just throw a whole, unpeeled potato into a stew, right? You need to peel it, chop it, maybe even season it first. That preparation is crucial for a good result. Similarly, with integration, we often need to prepare the integrand, that's the function inside the integral sign, before we can actually integrate it. Just as you cannot cook a whole vegetable without peeling or chopping it first, you cannot integrate certain complex functions without first preparing the integrand. This is just reinforcing that analogy. Some integrals are just too messy to tackle directly. We need to tidy them up first. Now let's get to the core of how we prepare. The primary goal of this manipulation is to rewrite the integral into a form where, and here's the key, a part of the integrand is a known function f of x, so we want to identify a piece of the integrand that we recognize, a function we can work with. We'll call that function f of x. And another part of the integrand is the derivative of f of x. This is super important. We're aiming to get the integrand looking like it contains both our function, f of x, and its derivative, which we write as f prime of x. Remember from your calculus lessons that f prime of x represents the rate of change of the function f of x. Okay, so let's move on to slide 2. This slide really helps solidify why we're doing all this algebraic manipulation. Why is this so important? Well, as we discussed briefly on the first slide, this setup is perfect for U substitution. If we can get the integral into this form, we've essentially set ourselves up for a much easier integration process. We'll see this play out in the example on the following slides, where we'll actually do the manipulation and then apply the substitution. So keep this slide in mind as we move forward. It's the why behind the how of algebraic manipulation. Common techniques. Okay, so we've discussed that sometimes we need to prepare an integral before we can easily spot a substitution. Think of it like prepping ingredients before you start cooking. Now, this slide outlines some of the most common algebraic techniques we use to do that preparation. Let's go through them one by one. The first technique is converting trigonometric ratios. What this means is, if you see a trigonometric function like tangent of x, it can often be helpful to rewrite it in terms of sine and cosine. Remember that tangent of x is equal to sine of x divided by cosine of x. This can sometimes reveal a structure that makes a substitution obvious. Next, we have adding and subtracting the same term in the numerator. This might sound a bit strange, but it's a really powerful trick. The idea is to cleverly add and subtract a term within the integrand, the function we're integrating, to create a part of the integrand that is either the derivative of another part or can be easily manipulated to become so. We'll see this in action on the next few slides with a detailed example. It's all about strategically rearranging things. Finally, we have multiplying and dividing by a constant. This seems simple, and it is. Sometimes, multiplying and dividing the entire integrand by a constant can simplify the expression or reveal a hidden derivative. It doesn't change the value of the integral, but it can make it much easier to solve. These are the main tools in our algebraic manipulation toolkit. Don't worry if they don't all click immediately. We're going to practice applying them in the example that follows, and you'll start to get a feel for when and how to use each one. Remember, the goal is always to rewrite the integral in a form where we can clearly identify a function and its derivative, setting us up for a successful substitution. Detailed example: integrating \int frac 1 plus tan x dx. Okay, let's look at this integral. Integral of 1 over 1 plus tangent of x, with respect to x as we discussed in the previous slides. The core idea behind substitution is to spot a function and its derivative within the integral. Now, if you look at this integral, it doesn't immediately scream substitution at you, does it? Let's break down why. If we consider the expression inside the denominator, 1 plus tangent of x, its derivative would be secant squared of x. That's 1 over cosine squared of x. Notice that secant squared of x isn't present anywhere in the numerator of our integral. Remember, for a simple u substitution to work effectively, we need that derivative, or something very close to it, to be present so that it cancels out nicely when we differentiate. Because the derivative isn't readily available, we can't directly apply the substitution technique. This is where algebraic manipulation comes in, which is what we've been preparing for. We need to first rearrange or transform this integral using our algebraic tools and trigonometric identities to reveal that hidden derivative. So, the next few steps will focus on manipulating this expression to make it substitution-friendly. We're essentially preparing the integral, much like a chef prepares ingredients before cooking, as we discussed earlier. We'll see how we can rewrite it to get it into a form where we can easily identify a function and its derivative. Step 1. Convert to sine and cosine. Now, the first step in this manipulation is to express the tangent of x in terms of sine and cosine. Remember from your trigonometric identities that tangent of x is equal to sine of x divided by cosine of x. So, what we're doing here is simply replacing tan x with its equivalent sine x over cosine x within the integral. This gives us integral of 1 over 1 plus sine x over cosine x. With respect to x, this might seem like an extra step at first, but it's setting us up to simplify the expression further, as you'll see in the next slide. By converting to sine and cosine, we're aiming to create a form that's easier to work with and will eventually reveal the potential for substitution. We're essentially preparing the integrand, just like preparing ingredients before cooking, as we discussed earlier. Okay, so let's move on to slide 5. As we discussed in the previous slides, we're tackling this integral. Integral of 1 over 1 plus tangent of x. With respect to x, we identified that a direct substitution wasn't immediately obvious, so we need to perform some algebraic manipulation. Step 2. Simplify the fraction. What we're going to do now is find a common denominator within the denominator of the main fraction. Currently, our integral looks like the integral of 1 over 1 plus sine x over cosine x. With respect to x, if you look closely, we have a fraction within a fraction. To simplify this, we need to combine the terms in the denominator. Remember that 1 can be written as cosine x over cosine x. So, we rewrite 1 plus sine x over cosine x as a single fraction with a common denominator of cosine x. This gives us cosine x plus sine x, all divided by cosine x. Therefore, the integral becomes the integral of 1 over this new fraction, which is cosine x plus sine x, all over cosine x. Now, to get rid of that complex fraction, we simply take the reciprocal. Dividing by a fraction is the same as multiplying by its inverse. So, 1 divided by cosine x plus sine x over cosine x becomes 1 multiplied by cosine x over cosine x plus sine x. This simplifies our integral to the integral of cosine x over cosine x plus sine x. With respect to x, this is a crucial step, because it sets us up for the next algebraic trick we'll use on the following slide to make the substitution more apparent. We're aiming to get the numerator to resemble the derivative of the denominator, and this form brings us closer to that goal. Okay, so let's move on to slide 6. As you recall from the previous slides, we were working on the integral of 1 over 1 plus tangent x. We converted the tangent x into sine x over cosine x, and now we need to simplify this fraction further to get it into a form where we can potentially apply substitution. Step 3, the algebraic trick, adding and subtracting. Okay, let's move on to slide 7. As we've seen in the previous slides, we're trying to integrate the integral of 1 over 1 plus tangent x. We've already done some initial algebraic manipulation, converting the tangent x into sine x over cosine x and simplifying the fraction. Now, we're at a point where we need a bit of a trick to make the substitution work smoothly. So the first line says, to make the numerator look like the derivative of the denominator, we use a clever manipulation. Remember, our goal is to get the numerator to be exactly the derivative of what's inside the denominator. That's the key to a successful U substitution. The next line reminds us that we know that the derivative of cosine x plus sine x is negative sine x plus cosine x. It's crucial to recall basic differentiation rules. If you differentiate cosine x plus sine x with respect to x, you get negative sine x plus cosine x. Keep that firmly in mind. Now hear us where the clever bit comes in. The slide states, we can rewrite the numerator, cosine x, by adding and subtracting sine x, and then multiplying by 1/2. This might seem strange at first, but it's a common algebraic technique. We're essentially creating a zero, because if you add and subtract the same thing, you don't change the value of the expression. Let's break down the equation. Cosine x equals 1/2 times the quantity of cosine x plus sine x, plus cosine x minus sine x. What we've done is cleverly split cosine x into a combination that includes the denominator, cosine x plus sine x, and something that looks like its derivative, cosine x minus sine x. Finally, the slide shows us substituting this back into the integral. So, we now have the integral of 1/2 times the quantity of cosine x plus sine x, plus cosine x minus sine x, all divided by cosine x plus sine x, with respect to dx. This looks a bit messy, but trust me, it's setting us up for a much simpler integral in the next step. We've successfully manipulated the numerator to include a form of the derivative of the denominator, which will allow us to split the integral and apply our substitution technique. In the next slide, we'll see how this all comes together. Step 4, split the integral. What you see here is a distribution step. We have 1/2 multiplied by the entire integral, and inside the integral, we have two fractions being added. Remember, in the previous step, we rewrote the cosine x as 1/2 times the sum and difference of cosine x plus sine x. So let's look at the first part. We're distributing that 1/2 across the numerator. That means we multiply 1/2 by each term inside the numerator, which gives us 1/2 integral of cosine x plus sine x, all divided by cosine x plus sine x. Notice what happens next. The cosine x plus sine x terms in the numerator and denominator cancel each other out, leaving us with simply 1/2 integral of 1 dx. This is great because the integral of 1 with respect to x is just x. Now, let's move to the second part of the split integral. We have 1/2 integral of cosine x minus sine x, all divided by cosine x plus sine x dx. This second integral is where our substitution will come into play in the next step, as we'll see. Okay, let's move on to slide 8. As you recall from the previous slides, we were working on integrating the function 1 over 1 plus tangent x. We've done quite a bit of algebraic manipulation to get to this point, and now we're going to simplify things further. So, to recap, by distributing the 1/2, we've successfully simplified the first part of the integral to a very easy integral of 1. The second part is now set up nicely for us to apply a U substitution. We're essentially breaking down a complex integral into two parts, one that's straightforward to integrate and another that requires a bit more work, but is now manageable thanks to our algebraic manipulation. Step 5. Apply substitution to the second part. So the first bullet point says, for the second integral, let t equal cosine x plus sine x. What we're doing here is defining a new variable, t, and we're setting it equal to the expression cosine x plus sine x. This is the core of our substitution. We're hoping to simplify the integral by changing our variable from x to t. Now the next part is crucial. It says, differentiating both sides with respect to x. Remember from calculus, when we have an equation and we differentiate both sides with respect to a variable, the equation remains equal. So, we're finding the derivative of t with the respect to x, and also the derivative of cosine x plus sine x with respect to x. The next line shows the result of that differentiation. The derivative of dt by dx equals negative sine x plus cosine x. Let's break that down. The derivative of cosine x is negative sine x, and the derivative of sine x is cosine x, so, combining those, we get negative sine x plus cosine x. Then we have dt equals cosine x minus sine x dx. This is a very important step. Remember that dt by dx represents a rate of change. To get dt by itself, we multiply both sides of the previous equation by dx. This gives us dt equals cosine x minus sine x dx. This dt is what we'll substitute into our integral. Finally, the last line shows the substitution in action. Now, substitute these into the integral. Equals 1/2 integral of 1 dx plus 1/2 integral of 1 over t dt. Notice how the cosine x minus sine x dx has been replaced with just dt in the second integral. This is the power of substitution. We've transformed the second integral into a much simpler form, the integral of 1 over t with respect to t, which we know how to solve. The first integral is also straightforward, the integral of 1 with respect to x. Okay, let's move on to slide 9. As you'll recall from the previous slides, we were working on integrating the function, and after some algebraic manipulation, we arrived at an integral split into two parts. Now, we're at a stage where we can actually apply the substitution we've been preparing for. So, by making this substitution, we've turned a tricky integral into something much more manageable. In the next slide, we'll finish the integration and get our final answer. Step 6, Final Integration. So, looking at the slide, the first thing we do is integrate both terms. We have 1/2 times the integral of 1 with respect to x, plus 1/2 times the integral of 1 over t with respect to t now. The integral of 1 with respect to x is simply x. And the integral of 1 over t with respect to t is the natural logarithm of the absolute value of t. Remember, we always include the absolute value when dealing with logarithms to ensure the argument is positive. Therefore, this gives us 1/2 x plus 1/2 times the natural logarithm of the absolute value of t. And crucially, we must add our constant of integration, which we denote as c. So, we have 1/2 x plus 1/2 log absolute value of t plus c. But we're not quite done yet. Remember that t was just a substitution we made to simplify the integral. Now we need to substitute back the original expression for t in terms of x. Recall from slide 9 that we defined t as cosine x plus sine x, so we replace t with cosine x plus sine x. This gives us our final answer. 1/2 x plus 1/2 times the natural logarithm of the absolute value of cosine x plus sine x, plus our constant of integration, c. Okay, let's finish up this integral. As we've seen in the previous steps, we've skillfully manipulated the original integrand to a point where we can now easily integrate. And that completes the integration. This demonstrates how algebraic manipulation can unlock integrals that initially appear quite challenging. Now, let's move on to slide 11, where we'll discuss some common mistakes to avoid when tackling these types of problems. It's important to learn from potential pitfalls to ensure accuracy in your calculations. Common mistakes to avoid. Okay, let's move on to slide 11. This slide highlights some common pitfalls students encounter when tackling these types of integration problems, and it's really important we address them now so you can avoid making these mistakes yourself. 1. Immediate substitution. The first mistake is jumping into a substitution too quickly. Many students, when they see the expression 1 plus tangent of x, will immediately think, okay, let's try substituting u equals 1 plus tangent of x, and that's not necessarily wrong, but it's often unhelpful. If you do that, you'll find that the differential, which is do, becomes secant squared of x times dx. Now, look back at our original integral. We don't have a secant squared of x in the numerator. Introducing that term actually makes the integral more complicated, not simpler. Remember, the goal of substitution is to simplify the integral, not to make it worse. So, resist the urge to substitute until you've done some algebraic manipulation to set it up properly, just like we did in the example. 2. Sign errors. Next, let's talk about sign errors. When we were manipulating the integral to get it into a form suitable for substitution, we dealt with expressions like cosine of x minus sine of x. It's incredibly easy to make a mistake with those signs. Always double-check your work, especially when dealing with trigonometric functions. Remember, the derivative of cosine of x is negative sine of x. Keeping that straight is crucial. A simple sign error can throw off your entire calculation. 3. Forgetting the constant. This is a classic mistake, and it's easy to do. After you've integrated everything and have your final answer, don't forget to add the constant of integration, which we denote as c. This represents the family of all possible antiderivatives, and it's essential for a complete and correct solution. It's a small detail, but it can cost you points on an exam. 4. Ignoring the coefficient. Finally, let's look at the example we just worked through. Remember how we used the trick of adding and subtracting the same term? We multiplied by 1/2 to achieve that. It's surprisingly easy to forget to carry that 1/2 through the entire calculation. If you do, you'll end up with an incorrect final answer. Pay close attention to any coefficients you introduce during algebraic manipulation and make sure they're included in your final result. So, keep these common mistakes in mind as you practice. Now, let's move on to the final slide where we'll summarize the key takeaways from this lesson. Key takeaways. Okay, let's recap everything we've covered and solidify the key takeaways. This slide summarizes the core principles of algebraic manipulation for substitution. Pause. First point, preparation is key. Remember, we started this whole process because sometimes the substitution isn't immediately obvious. We saw this in our example with the tangent function. If you don't see a direct path to a u substitution, don't force it. Instead, think about rewriting the integrand, the function inside the integral, using trigonometric identities or other algebraic techniques. This is like getting all your ingredients prepped before you start cooking. It makes the integration process much smoother. Pause. Next, target the derivative. This is crucial. The whole point of all this manipulation is to strategically rewrite the integral so that the numerator, the top part of the fraction, becomes the derivative of the denominator, the bottom part. Think back to the standard integral we often encounter. Integral of f prime of x divided by f of x dx. If you can get your integral into that form, you're almost home free. Pause. Now let's talk about the add and subtract strategy. This is a really powerful technique we used in our example. Sometimes, adding and subtracting the same term within the integrand can unlock the substitution. In our case, we added and subtracted sine of x to the numerator. This allowed us to split the original complex integral into two simpler integrals. One of them, integral of 1 dx, was trivial to solve, and the other was perfectly set up for a u substitution. Essentially, we broke down a complicated problem into manageable parts. Pause. Finally, standard form. Keep this in the back of your mind. After all the manipulation, many of these integrals will eventually simplify to the form integral of f prime of x divided by f of x dx. And as we know, the integral of that is simply the natural logarithm of the absolute value of f of x, plus the constant of integration. See, so, recognizing this pattern can save you a lot of time and effort. Pause. So, to reiterate, prepare the integrand, target the derivative, use the add and subtract strategy when needed, and always be on the lookout for that standard integral form. Mastering these techniques will significantly improve your ability to tackle complex integration problems. Are there any questions about these key takeaways before we move on to practice problems?